It's a bit loud. It's a bit loud. Yeah. Tell me when it's good. I'm gonna speak in and just tell me when the level's like there.
Yeah.
Okay. Yeah.
In the middle.
Before the middle. Ok, mais je vais le faire sur la caméra. En passant, on va passer au setter, prendre des piles. Oui, donc voilà, je parle dans le micro. Est-ce que c'est bon? Oui. Ouais. Je l'éteins? Je l'éteins ou je laisse allumer le micro? J'éteins le micro ou je le laisse allumer?
All right. Our next speaker is Srinivas Kalaga from Samsung, and he's going to show us dual Android on a Nexus 10 running on top of XEN. And go ahead.
Service solution. So a mobile operating system, what it requires. Yes. Okay. So a mobile operating system's requirements are quite different. Basically, the human interface that goes with the device is of higher importance. The touch, the user input has to be more responsive so that the customer does not feel that, okay, the virtualization is not hampering the performance. So the basic challenge for getting a virtualization solution to a commercial grade device is all about getting the user interface to the right solution. So our main research area has been to get the virtualized GPU running and check the performance, how it compares to the native device. So over the last 2 years, we have been working on Nexus 10, which was the first Cortex A15 based device that came out in market that supported virtualization extensions. So as you see, the Nexus 10 device, it's based on Samsung Exynos 5250. It has a dual-core Cortex A15 with virtualization extension, and it has a Mali T604 as the GPU. And the memory that's available is 2 GB of RAM, which was pretty high in early 2000, late 2010, early 2011. And the resolution is massive. It's 2560 cross 1504. And the amount of GPU throughput that has to go through for such a resolution and the bandwidth that's required is quite high. So if we could get a decent performance of a virtual GPU on such a device, we would be able to get to a commercial grade device to some extent. So that was the basic idea when we started off. So my presentation would focus on what we did and what are the challenges that we faced in getting a virtual GPU on a Cortex A15 based solution with virtualization extensions. So let's start off. What is the configuration of the device? So if you are familiar with XEN, you might be knowing DOM0 is the primary OS which does control and configuration. So to make our life easier, we got the DOM0 to run a full-fledged Android. And DOM-U is the second Android, which is a completely virtual Android running a virtual CPU. Even DOM0 runs a virtual CPU in this case. Mostly the I/O is completely virtual as far as DOM-U is concerned. I'll show a slide how the whole architecture fits in. And we used Linux 3.4. That was the version that was released with the device. And it was running, and it still runs, Android Jelly Bean 4.2. And we used Zen 4.2 as the base, and we went on to develop all the extension support. And I'll not go into details of the real virtualization extension support. I think we have other presentations which will, I think, go into detail. And as you see, the virtualization extensions, basically the ARM provides the virtual gig for the interrupts management, a two-stage translation page table so that the memory is clearly segregated and there is isolation of memory within the guests. And we have a new generic timer interface for the hypervisor timer, and we had to support virtualization for the Neon SIMD support. And this device has IO MMU, but it was not completely supporting second stage translations. So we had to use the intermediate physical address, which is the second stage translation address as a physical address. So that was basically the work which we did. I'm not going to detail of that work. My focus is mostly on the GPU part. And this development was done in collaboration with the Samsung HQ in Korea. So as you see the configuration, the DOM0 kernel has been assigned 1 GB of RAM, DOM-U 1 GB, and the Zen is fully SMP aware, supports full SMP. DOM0 was also supporting SMP. And the demo which we have supports single core DOM-U, but we have made lots of changes, and the DOM-U now supports multi-core as well. The main difference, which I would like to emphasize here, is that DOM0 kernel, all the IO devices are passed through, and the DOM-U kernel uses the PV drivers. So this is the whole configuration of the device. So this is the block diagram which I was talking about. So we call this PVH. I'm not sure how relevant it is. So the para-virtualization is for the IO part, and the full virtualization support is for the CPU and memory. So if you see the block diagram, the DOM0 kernel is on the left. The ARM's different execution modes there's a new hype mode where the hypervisor runs. And we have the kernels running in PL1 mode, and all the user land runs. The good thing about virtualization extension is all the user land run without any changes. So there are unmodified guests. The changes that happen is for IO devices. That's for para-virtualization. The CPU part of the kernel doesn't change at all. The memory management doesn't change. So if you see the IO devices, the Mali, touch display, everything is para-virtualized. And we have the virtual CPUs running on Zen. So this is the basic architecture of the whole system. So what are the challenges? I mean, the challenges for virtualization for a mobile device is primarily the IO. For a virtualization on a server, basically you handle the block drivers and network drivers. The workloads are different. So basically you focus on those two types of IO. But for a mobile device, tablets as well, we have tens of IO devices. We have lots of sensors, we have media, display, camera, we have connectivity. So all these drivers, you can emulate and trap them and put them completely in the hypervisor. But will it be feasible? Will it be practical? The testing time, the development time would be enormous. So the easiest solution and the best solution which then provides is para-virtualization, where the devices, the native devices still remain unchanged, run in DOM 0, and the virtual drivers use the para-virtualization bit. So a brief, so I'll be showing a video. Before that, a brief synopsis. So we have this, so there's something called arbitration engine which we developed. The arbitration engine, basically what it does is, at a time only one OS will be visible to the user. So this is a foreground domain which we call. So all the human interface parts, the display, the camera, the touch, everything would be assigned to one particular OS, one particular foreground domain. So the arbitration engine keeps track of which is the foreground domain and just manages the IO devices and assigns a particular device to a particular OS. So we have a display switch, which could be a simple app which we have developed, or it could be a physical button which can trigger a change in the domain. So before I show the video, so that it's quite clear what you see, the DOM 0, the main Android, would be of blue wallpaper, and DOM U will be of orange wallpaper. And we will be switching between the two domains using the icon and also using volume button. We have annotated the video so you can clearly see. So basically what we are showing is a lightweight game, Angry Birds, running in both the domains. And it's, I mean, with PV drivers, the performance is nearly native. And we'll also run Angry Birds simultaneously to show that the GPU is fully loaded and the performance is not degraded, though you use GPU in both the domains. And we have industry reference 3D benchmark, which we'll show and show the performance as well. This is the DOM 0. The performance is native because we use fast-through GPU. This is DOM U, the virtual Android, completely virtual GPU. If you see the transitions, they're as good as DOM 0. So this is Angry Birds running nearly at the native performance, which is 60 FPS. So we switch to DOM 0 using the volume button as a physical button. And we run the Angry Birds here as well, concurrently. We move to DOM U now. Angry Birds still running, the performance is still native. So both the domains are running concurrently. We stopped Angry Birds and DOM 0 now. Switch to DOM U. This is the industry standard GL benchmark. So the performance is around 35 frames per second, because the amount of GL calls that go through are immensely huge. But still, you can't perceive the difference actually. The frame rate is quite good. So DOM 0 is still running, it's rendering. DOM U is still running the benchmark. So this is the video which you want to show. If you see, the performance is quite good. So what are the challenges that we faced in getting this solution running? See, the Android Jelly Bean as an OS has introduced lots of changes to get a buttery smooth performance. So it has introduced a triple buffering and has changed the memory allocation schemes. It has introduced new memory allocators. FBDev was removed. They introduced new sync mechanisms so that the buffers are in sync across all the compositors. And they introduced hardware composition to reduce the burden on the GPU. So essentially what's happened is everything has been closely integrated. It's no more just limited to one subsystem of the whole OS. It's a combination of all those things. So to get the best performance in a virtual GPU, we did not change anything in the user land part. Only the kernel subsystems like ION, allocator, fence, and display drivers, these are the main kernel subsystems which were para-virtualized, and the data moves to DOM0 to the native drivers and then gets displayed or goes to the GPU. So we basically did the para-virtualization of ION, fence, and other things using grant memory and event channels. So the basic challenge here is to get near native performance, which is 60 frames per second. So as you see, the GPU first renders into a surface, it composites and creates a frame, and the frame has to travel back again to DOM-U, and then it goes to the virtual display, and then comes back to DOM-0, and finally gets rendered onto the real display screen. So the approach which we took is called API remoting. There's a reason why we took this approach. As an OEM, Samsung works with different chipset vendors. We have different graphics vendors like NVIDIA, Qualcomm has its own, Imagination, Mali. So all these silicon vendors have different drivers. Now if we start para-virtualizing these drivers, the amount of workload would be immense, which we wanted to avoid. So we came up with a different approach. It's called API remoting, where we take the GLES OpenGL ES APIs and we do remoting. So all the work is done in the user land and none of the drivers are changed. But still the performance has been quite good. So the Android's Jelly Bean's Buttermilk Smooth technology, which is triple buffering, VSync interrupts. So if you see the VSync interrupt, it's a virtual interrupt in DOM-U. So we use Xen event channel, and when we run a benchmark, the amount of events that pass through are immense. So the event channel is quite stressed. So we had to do some optimizations to make sure that we don't miss VSync interrupts and the performance does not deteriorate. So if you see in this example, the diagram shows how the fences. So this is the basic launcher. When launcher runs, if you see the fence mechanisms, each fence is allocated to a buffer, and we have to make sure that all the fences are waited upon and released at the proper time so that we don't lose any frames. So the basic challenge was to optimize this part so that we don't miss any frames. So these are the results of all the apps that use graphics GPU. If you see the DOM0 and DOM-U's performance for real-world use cases like Launcher, Gallery, Angry Birds, Gears, the performance of DOM0 and DOM-U has been quite similar, almost 60 FPS. And if you see the packets per second that go between DOM0 and DOM-U for the number of API calls that get remoted, as the benchmarks become more and more intensive, the event channel gets stressed and the performance comes down. So that's basically on all the apps which use the GLES APIs a lot. But still the performance for the real world use cases is quite good. So this diagram shows the event channels, the inter-domain events for VSync interrupt, which fires every 16.6 milliseconds. If you see, when the stress is very high, we lose some events, which makes us lose some packets, bringing down the performance. So XEN for mobile. So what are the things that we changed? We had to change the multi-page ring to ensure low latencies. And we found with non-leaded grants, and we fixed that. And as I said, the per VM interrupts are quite unreliable when they're stressed. So we had to reduce the scheduling latencies in some cases and do a shed yield so that we don't miss any of the interrupts. And we have been contributing, and idea is to contribute. It's a work in progress. we would like to contribute some of the code, at least the kernel part and the hypervisor part. The user land is again a little bit proprietary because a lot of work has gone into it. So what's the conclusion? The conclusion is, yes, it's definitely possible to take a server class hypervisor like XEN, and with the right changes in the I/O drivers, definitely it's possible to run full-fledged mobile operating systems to a decent level of performance. So XEN runs well on mobile devices, and using PV drivers, I think it's possible. No major changes are required in XEN architecture. So yes, I've taken 20 minutes. So that's the end of my presentation. If you have any questions and answers, I can take them. Yes, the question is, when would we release the patches? The idea is, yes, definitely we would like to. It's a work in progress. In the next couple of, I think, months, we are trying to push the patches. This is only for the kernel part. The GLES API remoting, which we did in the user land, I think it's again proprietary, which does not come into the GPL license. So that will not be released. But the rest of the I/O devices that we have para-virtualized, yes, definitely we'll push them. The idea is to push as soon as possible. We don't have any time frame, unfortunately, because we follow a different process for pushing the patches. Please go ahead. Pardon? I'm not sure. Yeah, I'm not sure. This is basically an R&D project that we did. Commercialization is, there are lots of other challenges. The power management, for example, it's one of the main critical issues that's still being looked into. So still in advanced R&D stage. Commercialization is not yet. Yes, please go ahead. 5420, not yet. Not yet. Yes, big little, yes, virtual. The work is going on that, but the problem there is the use case changes there because we have 8 cores, 4 plus 4. You can pin some CPUs, you can do lots of mix and match. So yes, definitely work is going on there, but exactly what's going on is still not, what can be achieved, it's still not clear. Please go ahead.
If we share the GPU between the two domains, we can one VM access the screenshots of the other VM. It may be considered as a security issue, or?
Yes, definitely. Definitely not just the frame buffer, the buffers. Any memory of a particular domain is isolated. So idea is to keep them isolated. So if a buffer belongs to a particular domain, the IO memu makes sure that sits to the same domain. So idea is not to share the memory. Even if a particular frame is displayed on the display, the display is independent. It might not interfere with other domains operating system and its memory. Yeah. Yeah, please go ahead.
Have you tried more than 2 VMs?
Yes, so the idea, yes, the question is, have we tried more than 2 domains? Not on this product. So we are planning to have DOM0, which is an independent driver domain, and run VM0 and VM1, which are DOM0 and DOM1 independently. Yeah. Yes, that's the work. Yes, yes. So the question is the power management, how will it be dealt with? So power management is a system-wide solution. So earlier, each OS used to take care of power management on its own. Now the work has to be delegated to hypervisor as well. So we'll have to introduce new set of hypercalls. For example, the frequency scaling and the low power modes. For each vCPU, they're going to be different. So we'll have to introduce new hypercalls so that there is a clear interaction between the OS and the hypervisor, and the system-wide decision is taken. Yeah. Yes. Yeah. Yes, Kapil, go ahead. I'm not sure. I could not get the question completely, to be honest. So I'm not sure about other products. Can you please clarify the question? Firefox. No, I'm not sure about that. Thank you. Any more questions? Storage? No, not yet. I think we are still in the research stage, so we are not sure how to address those real cases. Okay, thanks a lot. Yeah, please go ahead. Just last question. Yeah, just the last question. Sorry, I'm not able to hear it. Sorry, I'm not able to hear. Can you please?
Can you run something else with Android? Can you run Linux in the VM?
Yes, we can run any other operating system. But the idea here was to store the GPU's performance. But there's no limitation that we cannot run any other OS.
You're not limited to...
No, not limited, yes. Thank you. Yes, please.
What kind of use cases did you have in mind to run two Androids on a mobile device?
Yeah, the use case is the BYOD, bring your own device, run a personal OS and a commercial OS. So, for example, a company provides its own OS. It runs completely as a virtual OS. It can have its own enterprise apps, Outlook or whatever it is. So it's basically security to avoid malware getting into other OS. So that's the primary use case.
DOMU is still running while DOM0 is running also.
Yes.
Is it possible in DOMU to bring a web application server inside of it?
Yes.
And to have in DOM0 the web browser connected through the internal network,
Yes.
through a local IP network in between?
Yes,
and
it's
so
possible.
The web server on the DOMU will respond to the request provided by the DOM0?
Yes, so that's the approach we have taken for the ADB. For example, the ADB has to work on both the domains for debugging. So we use the IP packets. So ADB server still runs in DOM0, but DOMU acts as a client and reads the messages. So same concept can be applied
It's
to.
always running in the background, even if it's a scheduler is running.
Yes, so the power management part, if the domain is idle for a long time, you can put it to low power modes and wake it up only when it has.
Okay. So, I guess that.